Okay, hello everyone. Good afternoon, good evening. So my name is Onur. I'm from marketing. I would like to welcome you today's last session of the student webinar series HyperView. You must have received the materials. The link was broken, but I reached out to people individually who didn't have them. You pretty much know Garrett. You've been with him for the last 2 sessions. Today, however, Darius won't be here to take and answer the questions. If you have a question during the training, I'll try to forward them. I'll try to answer them. If you don't receive a reply from me, that means I'll forward your request and I'll be back with a reply maybe after the session or the day after. Or maybe Garrett will have time to answer everything. So yeah, that's all from me. Enjoy the last session, and the mic is on you, Garrett.
Oh, there we go. No, thank you for that. That was perfect. So definitely for today, I got no issue hanging around for a couple minutes to try to answer a couple questions that might be lingering, and certainly I'm going to do my best to keep an eye on those questions as they're coming in. Please be gentle with me if I don't get to you right away there. I might be intentionally leaving a question blank to get to it later, and certainly some things might come along the ways there. But I'm going to absolutely do my best for you guys to make sure we're keeping up with things there. So let me do this here. I'm going to pull up my screen, make sure I get everything showing correctly. Oh man, I swear I'm great with our products, but as soon as you get me using the other web companies, like in this case, LogMeIn's GoToWebinar, it's a totally different game on how my application skills are. There we go. Moment of truth. Okay, we got the right thing out. So we've had a good couple days together. I know we were off from one another yesterday there. It's good to get some maybe space from one another there to kind of digest some of our HyperMesh knowledge. But to kind of recap a little bit of Monday and Tuesday sessions together, I'm getting my days of the week correct. We spent a little bit of time going through certainly an overview of what's happening with SEA as a numerical method from a broader, more theoretical perspective. And I know that's so not sexy, and it's probably a little boring, and I'm sure when your buddies asked you what you were up to on Monday afternoon, they weren't too impressed to hear that you were learning about different mathematical methods to solve complex structural problems. But really having as much of an understanding as we can get our heads around, those are really the things that we're going to call on when we're in front of our own parts and it's time to mesh it ourselves. Knowing the scope of the analysis and understanding that our minimum element size is going to have an effect on the level of geometry and detail we can capture with the part. Knowing those little things is really the difference between just being able to technically mesh, but it's not very good nor very accurate, and really becoming an expert with these tools and someone that companies, your design teams, or whoever it could be is going to say, man, that's a user right there. That's someone that we really want to bring onto these engineering practices or these works for. So certainly don't ever, I would never recommend you guys to only think of these from an application standpoint, and any excuse we have to be kind of getting things back into more of the engineering world and not necessarily the application or the theory and the physics going on. That's certainly a standpoint that we're going to want to take on going through these parts. Now, outside of the theory, we spent quite a bit of time learning about the 2D auto meshing tool, as well as ways we can assess element quality. And what we'll remember from that, I'm going to actually pull up the model we left off on from Tuesday afternoon together. We'll remember from Darius especially was someone who is good about preaching this, that an easy way to assess your mesh quality is simply do the old eye test. And Darius had described it, and I would completely agree. If your mesh is relatively aesthetically pleasing, that's a good chance for it to be a high quality mesh. And the other half of that I can add in here is we'll also remember my little my mini lesson on this idea of mesh uniformity. And those of you that were good about listening or who remember from Tuesday that there were a couple different ways we could think of mesh uniformity. One of those being, are each of my elements as uniform and as identical as possible from one to the other? And at a little bit of a bigger scale, are features like fillets and holes being modeled and meshed the same way as they repeat throughout the part? both of those ideas of mesh uniformity are rooted in the same question or the same thought, really, and that you want as many apples to apples comparisons as possible in your FE work. You want to feel confident when we see results this afternoon together that those stresses I'm seeing in one element are comparable to the stresses in the other, and that I don't have to do any mental gymnastics to relate how those two stresses can be compared. We really just want to be able to take them at their surface value and say, that value is smaller for my stresses, that's the better design. That's how easy we want to make the interpretation steps for us. So, and frankly, and again, I know it's really tough to see without seeing a mesh, but when we get there together this afternoon, when you see those results, there's so much going on there, and you've already put so much work getting into it. We don't want to make it any harder than it is to be able to say, I know with confidence this is the best design, or I can tell you and look you in the eye with confidence that the car will make it 100,000 miles or cycles. Those are the sort of, we kind of want that kind of confidence when we're looking at the results there is what I want to get at with that. Now, I want to take a little bit of time today to walk us through some of the tools we have to actually help with element cleanup, because I know we left off Tuesday talking about different ways to say a mesh was meshed poorly or not meeting standards. One of those was with the element quality tool, the check elements tool, and I'm going to throw this in the chat window for everyone. Again, that was the F10 keyboard shortcuts for check elements. But we also had the F11 keyboard shortcut for the quick edit menu. So you remember that quick edit menu is where we had the toggle edge tool and some of those surface splitting tools that were really making our meshing easier. And then the final shortcut that I'm going to remind us of is the auto mesh tool itself is from F12. So right away, just a couple keys all within a couple millimeters of one another, depending on your keyboard size, gives you a lot of power from the software standpoint there. Now, coming into my F10 menu, like we saw Tuesday, I can come in here and set different thresholds for all of these different quality checks. And if we're not sure, maybe we're mixing up what one quality check is relative to another, we'll remember that F1 will always launch the help for the software, and it'll even bring you to the current tool you're in. So if I'm not sure how these quality checks are being managed, I can load up the help, which is F1, and it'll automatically direct me to the page that describes how each of those calculations are being performed. So if I wasn't sure what that Jacobian value was and what that means, I can come up here and quickly learn that the Jacobian was a measurement of how much a given element's shape in its area is deviating from the ideal 90-degree perfect element. So a 1.0 is 100% where the ideal shaped element, whereas 0 is none of the area overlaps between the ideal shape. That's a big problem there. That almost like an inverted element, I think, for a negative Jacobian. And it even lets me know in here that there's a couple recommended acceptable limits or some general values to shoot for there. And as a rule of thumb, I don't want to go too much back on what we covered Tuesday, but a good rule of thumb about mesh quality is your mesh is as only as high quality as the worst element. And some of the solvers do kind of literally behave that way, where you could have 100,000 out of 100,001 elements be very high quality, but one element be super ugly. And just for reference, for maybe some of us who are a little bit newer to FEA, things can get very ugly quick. I know what I got up here on the screen is not a sexy, good-looking mesh, and I got some real issues with what we're seeing here. That's technically a quad element that's being flattened to a tria, but it can get even uglier than that. Just as a very interesting example here, let me just turn around and take this quad element here and start to shrink this guy in. You could get some quad elements that look like this arrowhead little structure here where it's starting to kind of invert almost. You could see elements that will do something like this, and now it's truly overlapping itself. Now, these are things I would not expect to typically happen, but through a combination of some manual cleanup efforts like I'm showing here that I've picked up with my own expertise over the years and some funky geometry files, once in a blue moon, you can see some pretty catastrophic things there. So certainly something as porous as that, where there's intersections and overlaps and all sorts of twists and pretzels thrown in the mesh, a lot of times the solver won't even bother to go through with the rest of the job submission and just say, listen, man, the mesh you just gave me is trash, it's garbage, it's no good. I don't want to solve it. You got to fix this up. And usually solvers are good about telling you the element number that failed and little things like that. But that's the approach we want to take with it. So you might hear people talk about quality either in terms of its worst element, like I've described, or really another common scheme could be talking of element quality in terms of percentages of elements that meet a threshold. So I've worked with some of my customers that'll do it where they have a very strict quality requirement where 90-some% of the elements need to meet that requirement, and then the remaining 10% just needs to meet a very, very simple threshold just to ensure that it will pass the solver checks. So that's another way of thinking it, of a majority high quality element mesh with some poor elements. Some people only think of it in terms of a worst case scenario element threshold. Long story short, they're all coming back to the same idea. What can we do to ensure that we're getting as many of these perfectly lined up or as close to squares as possible and not this kind of junk here? So we saw on Tuesday, there's quick ways for me to use that F10 menu to identify, low Jacobian elements, and sure enough, those guys are getting called out. Or, there's ways you could check for element angles as well. I prefer to look for the skew. It's an easier way, but some people prefer to do it by element angles. There's no one correct way to do this. Now, but what I want to go through are what are the actual tools I have to fix this? Yes, I know it's broken, but I have no means. I'm useless. I can't actually solve it. And that's not how we want people to feel. And unfortunately, HyperMesh will never, knock on wood, hopefully it doesn't make you feel that disempowered with the tool there. We want to build you guys up. I want you feeling like a superhero when you're going through the tool. In my opinion, once you are in HyperMesh, it is the closest thing you will ever get to feeling like an Avenger. I could be totally wrong. I am not Robert Downey Jr., but I feel like a God-blessed superhero when I'm flying through with HyperMesh. And that should be everyone's goal in here. And I promise you, if you're struggling through it and you think, I know I can do this, I know I can get there, that light bulb moment, it's glorious, folks, and we're getting to it. Now, how can we actually get there, then? So what I want to show us next here, I'm going to take my Spotlight tool, and I'm going to come back into my 2D mesh menu here. I have shell elements on the screen. I have 2D elements. I want to continue to work with those. There's a very helpful tool with editing an existing mesh, and it's kind of hiding here in my second column to the right here. So again, I'm in that 2D menu, column over to the right here. There's a little hiding tool in here called Quality Index. Quality Index has a lot of great kind of macros built into it for us. Now, it is a two-part tool. It's kind of it's both whole and oats. It's not just one or the other. And how this tool works is it allows me to establish a quality threshold or a quality criteria that I'm interested in. So that it actually comes in here and lets me establish my quality threshold for failure. So I mentioned earlier that there's some files in there that you might remember from Tuesday that actually store this quality criteria, and it's that same file. So we learned about a preference and criteria file earlier on Tuesday that can be used to drive geometry cleanup. If you kind of recall back to Tuesday afternoon, you might remember a little lesson where I'd shown there were two files that work in tandem to describe how HyperMesh can automatically process and clean up your geometry before meshing. Well, those same files can also be used in a quality cleanup procedure. So if I actually come to my preferences pull down at the top of my software, hiding on this little list here is a criteria file settings option, criteria file for element quality criteria there. Now, there's a couple different ways we can establish criteria. The biggest two groupings are going to be whether it's a 2D element or a 3D element. Naturally, 3D elements are going to have all sorts of additional ways they could break. Now, our 2D quality criteria, though, these are the failure limits being established. So I'm going to bring that Spotlight tool back in here. This criteria file allows me to say, you know what, I wanted to mesh it with some average size. And from there, I can start bringing in a failure criteria. So if your boss or your design leader or some other manager of sorts comes up to you and says, hey, I need you to make this mesh for me in HyperMesh. I need you to use X millimeter elements, and here's the failure criteria. And they might tell you to make sure every element is at least a certain size. They might ask you to make sure that no element has an aspect ratio that exceeds a 10:1 edge length. And they might also ask you to ensure that none of your quad elements experience a warpage bigger than 10 degrees. Warpage being measured how out of plane is one of the 4 corners of a quad element relative to the other 3, or how flat is it. Now, if you know those threshold limits, or you have a couple standards, best practices that you set yourself, or these are things too that you could probably just do a quick Google search for, and basic mesh quality requirements. And I know there's all sorts of third-party literature out there, and hopefully you guys have been picking up some good ways to think of this while you're going through it. But you can actually set those threshold limits in here. So maybe I want to make sure all of my elements are at least 0.5 millimeter in size. I want to make sure my aspect ratios don't exceed 10, and I also want to make sure my warpage is no bigger than 10 degrees. I can establish those thresholds right in this file and hit OK. Why I bring that up is when I come back into my quality index tool, this quality threshold that it's showing here is pulling it straight from that file. So why I like this is if there's only a couple checks you're concerned with, right now we're just going to consider minimum size, an aspect ratio, and warpage, and I'll leave Jacobian in there too. We'll just do those 4. I can actually just turn off the rest for now. And now what I have is just a very easy way to assess my mesh quality. So actually what this tool is doing is it's updating the contour to show me elements based on their quality. Any yellow element in red has already failed the quality criteria. Any element in yellow hasn't directly failed it yet, but it isn't necessarily that high quality, and it's closer to failing than it is probably being perfect. So this is a cool tool to really help you identify where things are failing. And I know it's kind of grayed out on the screen, but at the top of my session here, it's also listing the number of elements that are failing each check. So I'm going to just come into that preferences menu and go to my colors options. And I'm going to not force those to be black. There we go. Hopefully that's a little easier to see now. So I can see here that most of my elements are above that 5 millimeter or 0.5 millimeter limit. Nothing has a bad aspect ratio exceeding 10, but there are a couple elements failing my warpage check and a couple elements failing Jacobian. So some very, very basic tips here for quality cleanup. Warpage is most likely occurring at curved surfaces, and that's very easy to understand in my opinion. Elements on a flat surface are never going to warp, they're going to stay nice and flat. You experience warpage because you're trying to model curvature with a limited number of straight edges, and those straight edges coming from your elements. So naturally, I'm expecting along my fillet faces or substantially curved surfaces where my warped elements are going to occur. So I can see that I have some 200 elements warping. I'm going to cheat here and just make that the only quality. And sure enough, all of my elements that are warping are virtually either at this curved region here we can come back on, this larger fillet here, as well as these fillets down here. Now there's something funky really going on with that mesh flow there. We're going to come back and investigate that. So as a rule of thumb, warpage is typically going to happen from curved areas. Now, if you have many, many elements on the same curved surface failing a warpage check, what that can be telling you is that you probably have too large of an element size to capture that curvature in a clean and accurate way. Let me demonstrate that for a moment here. I'm going to just hide my mesh here, and I'm going to just make a new component for reference. So this is just new component that we're going to refer to. And I'm going to start meshing that part again at just a couple surfaces here. So I made the separate component just so that way I could keep things clean. So one thing I hadn't mentioned yet is in your meshing tool, it'll always default with this option here labeled elements to surface component. What that's saying is as this meshing tool makes new elements, it'll place those elements in the same component that the geometry file belongs to. And that's great default behavior. That prevents you having elements in a separate component from the geometry of that component. Now, this is an example of where I want to keep it separate because I want to have a second mesh to play around with. But for the most part, it's very straightforward to keep those the same, and I would recommend you do so. But just for the sake of argument, I can also toggle this to allow my elements to be placed in a current component or an active component. Your active or current component is simply the one that is bolded in your model browser. So right here, we can see new components got that big bad bolded font. I could always select one of these and right click and choose the option Make Current to update that component. So what's nice about that system is it's very easy to control where you're placing things in your model browser, which component they belong to. And we're going to see in a moment, even though it's the pink component, I'm going to get elements to mesh in the green component here. So what I'm going to do is just throw on a sample mesh of a very coarse mesh size, maybe something like 25 millimeters here, an entire inch element. And I'm going to come over to this surface here, and I'm going to start meshing that. Now, certainly, it's very, very ugly. I'll give it the old college try to at least give it something that looks better here, and I'll talk about why in a moment this is meshing kind of ugly. But that is the couple elements I have to consider. And if I come back to my quality check tool with the old F10 and run that warpage check, I shouldn't be surprised, and I'm not surprised knowing what I know, I've done this a couple times, that those are warped elements. I'm asking a straight edge to traverse across a much bigger chordal region than the smaller element to approximate curvature. It's really no different than an exercise of trying to approximate a circle with 4 edges versus 8 versus 16 versus 64. And I think we'd all agree that you're going to have less angular deviation as you introduce more straight lines. So that same principle is happening here with warpage. So I just wanted to include that kind of thought process as an example of the more you start meshing, you're going to really start to build an intuition on why elements might be failing. And those are also going to start to become factor into your decision making on what your element size should be. So I'm seeing here from trying to mesh this with 25 millimeter elements that maybe that's a little too big. Maybe we need to refine it to reduce the amount of warpage those elements are seeing. So maybe I'll come back in here and just for the sake of argument, maybe bump that down to 5 millimeters now. And now all of a sudden, first off, it looks good on the eye test, and the eye test usually treats me very well. But I can also come in here and see that, well, there's a lot less warpage failing happening. And certainly, though, now, it's also okay, though, if not every element is perfect in its exact size either. It's totally okay if you're going through this and you find out, yes, I'd be willing to bet these very, very small 1 millimeter elements don't warp at all. And I only have one of these guys failing, and it's probably going to happen at the very end of the mesh. Yep, it's this very long one there. But just because none of these are failing doesn't necessarily mean this is an appropriate mesh either, because I'd be willing to bet we made these elements too small, or smaller than we really need to. As a general rule of thumb, you're not wrong for thinking that as your element size decreases, your solution accuracy goes up. So let's just pretend that we're only doing cantilevered beam models. And cantilevered beam models are nice because you can, for the most part, create them in the real world in a relatively easy controlled environment. You don't have to jump through that many hoops to create a cantilevered beam model in real life. So let's say we did one of those and we had the FE model for it. And now we want to compare our FE model to the deflections we saw with the real world model. What I would generally expect us to see as our element size decreases and our element count as a result of that starts to increase, your solution accuracy between the FE tool and the real world physics you model is generally going to go up to a point. At some point, you're not going to get any more accurate than you are, and your error percentage, so if on this axis I have some error percentage, or I guess it'd be 1 minus error percentage, and on this side you have 1 over your element size. So as I'm increasing on the x-axis on my very poorly drawn graph, I'm decreasing my element size, you're naturally going to get a more accurate solution. But again, I want us to be very aware of this idea up to a point. And some of you might be thinking intuitively, well, what is that point? Is that 5 millimeter elements? Is that 50 millimeter elements? Is that 0.05 millimeter elements? And it's certainly going to depend on the physics and problem. There's no one golden blanket be-all, end-all answer. But this does happen, this inflection point, or this plateau rather, happens at a little bit more of a coarse element size than you realize. I know when I was first learning this, I expected that value to be something on the much finer mesh size, like I'd shown in that last example. It tends to happen for a given structural model around 6 millimeters or 1/4 of an inch element size. So not as fine as you might think, which kind of brings up an interesting point of, well, we saw when I did 5mm elements, I don't have perfect element quality. And you're not wrong for thinking that, but ultimately, why I brought all that up is that it's okay if you don't have 100% perfect squares. The physics and OptiStruct of your solver can account for those slight changes. The most important thing is, like we were preaching on Tuesday, is consistency, and that you're making an honest attempt to model features the same way. You're making an honest attempt to make sure the elements aren't too crazily shaped. But after that, the physics are going to take care of itself. I know from learning this myself that there's so many different moving parts, and some of us still might be in school, going through our first couple static classes and our 200, 300 levels, and we might now feel totally confident with the engineering. Don't let meshing be the one thing that makes this difficult. I know it gets a bad reputation. I'm sure there's senior folks at all sorts of companies you may have interned at or worked at that are saying, oh, meshing's so hard, you got to be an expert to learn how to do it. I really don't think that's true. I think you just gotta, have a good head on your shoulders, use a little bit of common sense and good judgment, and the tools themselves can take care of it. So don't certainly get bogged down and need everything to be 100% perfect. Have a little bit of give when you're working on it. And I think it's a lot of these things will come with it naturally if you're not being too rigid with your mesh criterias and your quality requirements. Now, I promise you, we're going to learn some ways to repair these low quality meshes. And let's just do just that. So I'm going to come back to this real ugly pink guy here that I just took a fat chunk out of. And I want to come down to this region here where there's all sorts of nonsense happening here. This is some straight no good enough. So what I want to do is I'm going to navigate back to that quality index tool. And we've learned how I can pair this with my criteria file, and I can actually call out failed elements for all these checks. So I want to know my really small elements, my stretched elements in terms of aspect ratio or in terms of Jacobian, as well as my worked elements. So I got just a handful of checks up on the board. I got some warning elements and I have some failing elements here though. So it's good to see both there. Now, there's two ways to fix elements. And this is going to be approach number one we're going to learn about today. Quality index tool is great because it'll also do what we call element patching or isolating these regions of elements for us. So what I'm going to do here is I'm going to come over to the tool and I'm going to hit start. So what this is going to do, it's going to start cycling me through, and I can hit next and previous to go to the next patch of elements. So I don't have to spin my model and zoom in and out to find these. It makes hunting down those few failed elements very trivial for you. You shouldn't have to spend time doing the old spin around, zoom in and out, identify that one failed quarter element of 100,000 that gets it away. I've called out a few bad behaviors if I find you doing, not that I ever could, because I will most likely never meet the folks in this room. But if I do ever find you and I find you playing the needle in a haystack game trying to find a failed element, I'm gonna be in your ear a little bit about it. But fortunately, this patching tool takes away from ever having to find the needle in the haystack with your failed elements, because it allows me to just cycle through these. Not only that, hiding in the tool right under that patching tool are cleanup tools. These are really why we're interested in quality index. This is all pretty good. This is some lemonade in my opinion. I like lemonade, but it ain't making my day sort of thing. This is good stuff. It's helpful that I can help find my elements, but we already saw there's some other ways to do that. This cleanup tool business is really why we wanted to stop in the quality index tool. This gives me access to 10 different macros that can clean up all sorts of problems with 2D elements. Some of the things I have in here that I still, as a self-proclaimed HyperMesh expert, I use a lot of these in my own day-to-day. And some of the ones I like are this split quad element. We'll talk about why the node and element optimized tools are extremely powerful. And there's even a couple drag and collapse tools in here as well. So I'm going to start with node optimized and element optimized to start. These tools both require you to select the tool before you use it, and they might have a couple other options along in here that control how it behaves. If you have any questions on the details, I'm not an expert in all 10 of these, but if you ever want to know more details on what's happening, again, you can always hit F1 on your keyboard. That'll launch the help directly for the quality index tool. This will give you some help on how it's coloring things, how that criteria file is being referenced, as well as the cleanup tools there's a little page to redirect us to how all of these cleanup tools behave as well. You'll hear me say it over and over. Documentation is probably not something people were excited about when you're coming in here. One of the things that personally gets me excited about continuing to do work with Altair as a software company is our documentation kicks ass. I have to look at it all day and send it to customers and multiple times a day. It's very helpful. And again, you're not going to go brag to your buddies and talk to your parents about it. Oh, I was reading FEA documentation late at night. There's practical information you can pull out of there. And I think I'm very impressed by the work our documentation team does. It's not a lot of reading to get to the good stuff. It's just nuggets of gold and gold worth of information available to you that's always a click away. And even to this day, as once again a self-proclaimed HyperMesh expert, there's so much stuff in there that I'm continuing to pull up or find little details I missed the first time in those help menus. So definitely don't be shy. In fact, I think you're a fool if you aren't using F1 in those help menus while you're walking through the software. It's the easiest way to learn more and more information about the tool as you're learning it, is to continue to reference the documentation. Now, there's all sorts of tools in here, and I told us we're going to start with Node and Element Optimize. What these allow me to do is left click any of these elements, or a node optimizes a node, and it will slightly move the position of that node. Right now I have it to do it along the surface. It will reposition the node to cause the elements to change shape a little bit, and it will reposition it such that it gets the elements to their ideal quality or as close as it can be. So I can actually come in here and just start clicking away at some nodes, and it's going to start moving things around as it needs to. And I can even let it deviate a little bit to the surface by moving normal off the surface. You want to be careful with that. Or you could let it do both normal and tangential to the surface. So some ways you can quickly clean those up. I personally stay away from these normal too. I only do along the surface. I don't want to introduce additional warpage to my model, but sometimes that's a necessary evil. You know, get it 1 degree off plane just to avoid significant aspect ratio issues. You know, those are the sorts of things we can do. Now, a little more practical though is element optimize. It's the same idea, but it does all 4 nodes of one element. So I can come in here and just start clicking these yellow and red elements. And a lot of times, you know, you can get lucky and just 1 click fixes it. Now, the problem with these optimized tools is it can't always give you a good answer if the starting mesh was poor, like I'm seeing here. But that doesn't mean we're SOL. Because some of the other things I can do in here, excuse me, are splitting these elements. So I mentioned that there's an option in here called split quad elements. What this does, and this is a great solution for some warped quads. Now, I would never just automatically default to, I got a warped quad, I'm going to cut it in half, now it can't warp. That will work, but if you do that for every warped quad, you can essentially double your element count in the model. So what the split is really cool for is take an ugly quad like this that's really getting more trapezoidal or rhombus shaped than it is rectangular. And these are good ones to use the split tool on, because what it will do is it'll split it across one of its diagonals into 2 tria elements. Now, like I said, technically we went from 1 element to 2, and if we keep repeating that, you can really substantially increase your element size. Now, this model's probably got 15,000 elements. I don't mind just 1 element being added to it. It's a negligible difference in solution time and degree of freedoms. However, you also want to be careful that if you have so many warped quads that you want to split all of them, I wouldn't split them all. I would just go back and reconsider remeshing that entire surface with maybe a finer size to avoid the failure limit in the first place. So yes, this will prevent elements from failing, but we don't want to just blindly become the guy that meshes or the lady that meshes using only splitting our quads into triads and calling it a day. That is a horrible way to do things, boys and girls. If I catch you doing that, I'm going to get very upset with you, and I'm going to give you a tongue lash in that. Now, there's some other cool little tricks in here, and I don't want to do all of these tools, but there's a lot of stuff we can learn in here. And my favorite one I'm going to demonstrate here for a moment. I'm going to borrow a mesh over here. I'm going to go back to my quality index tool. There's a very fun tool called drag tria element on the far right. So I mentioned before that I spent quite a bit of time on Tuesday talking about that idea of element edge density and how we can adjust those in the mesh tool to make sure we have ideally uniform density across edges, and that helps us get in an orthogonal and a quad dominant mesh. Now, sometimes trias are a necessary evil for a given transition area, and there's a quick way to fix them if you forget to catch it in the meshing steps. So here, I didn't like that I introduced this tria element that I've highlighted in purple on the upper right. And I don't want to go back and remesh the surface now. I just want to fix it. So what this drag tria tool lets me do is click and hold that tria element, and I'm going to drag it while holding my left click. And it's like a zipper. It's going to open that up and just introduce all new quad elements that got meshed in there. Those also go the other way as well. So I can certainly keep going in this way, and like we saw, introduce it to the edge and add a quad. Or you could, what I call, close the zipper and also turn everything into a 1 to 2 transition up till you can. So there's a lot of cool stuff you can do with that tool. That took me probably 2.5 years of being on Altair to find that out. And I think I spent like my entire morning just playing around with that. It's very fun. And if nothing else, you can kind of show off to your friends, be like, look, man, look what I can do. I can make a mesh better than you. And then they'll have no idea what you're talking about, so it's okay. Now, the other approach, though, that I'd recommend to newer users for element cleanup isn't that quality index tool. I think what you guys should be taking away from this is a great local tool. This helps me with, a couple failed elements where I can come in here and do that element optimize or node optimize or split it in a worst case scenario to get 1 or 2 elements fixed. And that's 100% how this is intended to do. Now, if you have something like that first mesh we looked at, this pink boy, that had all sorts of ugly nonsense on it, what this is telling me, regions like this coming back to it, is something happened at the initial element creation, and I can almost guarantee you it'd be quicker to just try to remesh it than to go back and try to make it work with some cleanup operations. So what I would do for something like this is bring the geometry back into play in your model browser. So right now, why this display looks so ugly is because we have elements in geometry trying to overlap one another and doesn't always jive. And what I'm going to do here is I'm just going to come back to those surfaces that meshed poorly, and I'm going to try to mesh these again here. And this is where you can adjust the element densities on the fly as you need to, and there's all sorts of things we can do there. But also, this is where I'm going to just delete a few things out for a moment here. The reason why this also might not be meshing too cleanly, I'm sure some of you are screaming at your TV, or your monitor rather, is because of we haven't necessarily done cleanup on these surfaces yet. And that's 100% true. And I wanted to come back to this to bring that full circle. FEA is certainly more Ouroboros or a web than it is a linear chain. Everything feeds into itself, and there's so many interdependencies on how geometry affects mesh and little things like that there, that I want to come back into my quick edit menu here. And this is an example where we could have taken that same toggle edge tool we learned about on Tuesday. Maybe I just left click and turn off some of these edges that were screwing this up. Same thing here, same thing here. And now, just for the sake of example, we also learned we can manipulate things like points. So I'm going to use my add point tool to just specify those corners again on these edges here. So I'm going to undo that for a moment. This is a rare example where I have an edge with a sharp corner that doesn't have a corner node. You're seeing here how it actually didn't mesh all the way down to this corner. Well, that's because it doesn't know that's an actual vertex. This is you have to almost intentionally break it to be the case. But I can just go back in and make sure I add my own corners. So now when I go to mesh this, I see that the elements are going to deviate to those corners. So the lesson here isn't, yes, corner data is good. It should be that these point options in my quick edit menu, and again, this is that same F11 quick edit menu we've seen the last couple of days. This add remove point tool, what this really allows you to do is not just to find corners of edges, but literally anywhere you drop one of these points, whether it's in the middle of a surface or at the edge, it'll enforce a node to exist there. So this is a really good way to kind of manually control mesh flow if you need to. If you don't want to use surface splits, you could also use points to kind of like guide your mesh here. A cool little way to do that. And vice versa, sometimes there's points you might want to remove if it's forcing those to be at places you don't want to be. There's a little bit of creativity to that. Now, the final thing I'm going to do here is I like to do my own surface splits all the time. So I'm actually going to take a split from this corner that we defined, and I'm going to do that same idea of that line we turned off that goes up my screen, but I'm just going to do it as a node-to-node way that I'm going to define myself. And now you'll see that what's coming out of that operation, now that I have this nice straight line there, is hopefully we're starting to agree that, the mesh you can get now after just a little bit of cleanup in there is starting to look a little better. And that's the idea there. So don't be afraid. I would almost always recommend you take some time to review your geometry and surface lines before you mesh. Try to identify those ugly, really squiggly shapes. And frankly, this exercise 3A is like is a perfect lesson on how not to design a part with meshing in mind. Because there are so many things like these feature lines on a planar face that do nothing but break it up arbitrarily, that just get in your way. There's all sorts of problems with this from a meshing standpoint. And this is a really good thing to go back to and say, well, why was this so hard to mesh? Look at all these feature lines and start to ask yourself or ask your designers, make sure we're not drawing parts that look like this with all these unnecessary feature lines. I don't want to scare you from many surfaces. Sometimes you need detail and need surface lines, but you want to use them only as needed. I used to work for a guy when I was in high school that was like the closest thing, if anyone's ever seen the cartoon King of the Hill, to the character Dale Gribble. This gentleman lived in my neighborhood. He loved conspiracy theories. He is probably an insane person. He's a very nice man, though, and he gave me $10 a day to come help him out with his dog treat business he worked. $10 an hour. He used to work cash for this guy a couple hours a night. I'll never forget, though, the one thing this very strange man said to me. I'm still talking about it 10 years later to a group of strangers. Everything should be on a need-to-know basis. And I remember thinking how bizarre that was, and I don't necessarily agree with it. But when it comes to surface design, you should only include, edges and features as needed. You don't want to complicate your design any more than it needs to from a meshing standpoint, just to make things harder on yourselves. That's certainly not something we'd be interested in. So always remember that. Some strange man in my neighborhood when I was 16 years old telling me things are on a need-to-know basis. Your part design is on an as-needed detailed basis there. Don't just go in and add all sorts of complicated spline surfaces if you don't need them. If it's easier to design something as a conical feature, go for it. The more feature-based and simple it can be, generally the better and easier to mesh that's going to be there. So hopefully that kind of helps start introducing some of the ways you can adjust a 2D mesh and work with those 2D meshes there. Now, what I kind of want to transition into here is a very quick, streamlined lesson. I want to introduce the basics of 3D meshing, but I don't want to get too bogged down on that. And in fact, it's going to be very analogous to what we've done in 2D, just with a couple extra steps there. So what I'm going to do here is put this on the back burner. I'm going to come into my training files here, and I'm going to pull up a new lesson for us here. Let me get my HyperMesh folder. And our student exercise, I'm graduating up to the 3D meshing chapter here, and I want to talk about exercise 4A for a little bit here. So as a rule of thumb, and I think we're starting to see this, 2D geometry, we can use 2D elements for. And we're going to learn how today in a moment we can use a property card to give it that thickness and actually turn it into a 3D entity. But fortunately, for very oblong 3D objects like we're seeing here, and you'll remember from Tuesday I talked about this is a tricky part to mid-surface. We couldn't mesh this with shell elements. We're going to need 3D elements. And I think that's actually more intuitive. 3D meshing is almost extremely analogous to like building with Lego bricks as an example. You just have a small thing that connects to another small thing, and you do this enough times, it gives you a big thing. And that's really the rough idea with 3D meshing. And 2D, and we'll see that full circle in our next lesson, has one extra step before it truly becomes a volume. Now, what does that mean for 3D meshing, though? Well, this gives us an excuse to poke our head around into the 3D menu of HyperMesh. I'm sure you guys are shocked to learn that the 3D meshing tools are hiding here. And the one that we're going to really emphasize is going to be this TetraMesh tool here. Again, it's that second column to the right. It's called TetraMesh at the top. This is going to be the home for our 3D TetraMeshing. Now, if I pull up the slideshow for this particular training that we got going on in chapter 4. There are actually two schools of thoughts on how you can solid mesh things. The first school of thought is what we're going to cover together here, and that is what we call tetra meshing. Tetra being a tetrahedral element is a four-sided pyramid made up of just triangular faces. And naturally, they also have a pyramid element, it's kind of their brother element, which has a square base, but again, four sides of triangular faces. So the really only difference there being the pyramid has a square base compared to the triangular base. Now, the other school of thought, the rival, if you would, of tetra meshing is hex meshing or solid meshing. And those are our cubes and pie slice wedges. They are both 3D elements, and they essentially are doing the same thing. I would never sit here and tell you that one is more accurate than the other, or you always should do one for another. I don't want to get that specific, and that's generally not true. Really, why we have two different schools of elements comes into how these are created. We're going to learn that the first school of thought, tetra meshing, is probably the most flexible meshing tool in the FE world. Any 3D volume that just exists and doesn't have a hole in it can be tetra meshed. It can just always be done. It's great. You don't have to worry about anything going wrong. Hex meshing with these bricks and pyramid elements, or not pyramid elements, excuse me, the wedges, the very simple shapes, the cubes and wedges, they're limited to the designs and the volumes on how they can fill them up due to their shape. So not every part is technically going to be eligible for a solid mesh. And knowing that, I think it'd be more practical with our group to just go with the surefire way. I'm not going to have any problems. Now, with that in mind there, it's understandable some of you want to know, well, damn, if we can't do it for every part, why do we even have it at all? And really the idea comes down to you're able to mesh a volume with less elements using the hex and pent elements. Just not every volume can be meshed that way. So if you can do it, it tends to be a little bit quicker solution time with less elements. But on the flip side, it also takes a little bit more user experience to know how to get it to work because they're not truly automated tools there. And that's not a HyperWorks thing. That's something I've personally been interested in, and there really isn't in 2020 at this point a truly automated hex mesh tool. If you hear someone advertising that they have an automated hex mesh tool, approach it with a grain of salt because we've been looking at this, and I know third-party companies have been looking at it. No one's hit the jackpot with it yet, so don't be swindled into some back alley software licenses out of the old bootleg van. I don't know if you guys are old enough to remember the bootleg man, but once upon a time, there were gentlemen that would carry burned CDs and DVDs and bootlegs so that they would videotape at movie theaters very illegally, and they would just sell these bootleg DVDs out of the trunk of their car all around the neighborhood. I miss the bootleg man. He was great. That's how I got all my Adam Sandler movies growing up. I don't know what happened to bootleg man. Miss him. But don't buy software from the bootleg man. That's a bad idea. Now, I want to talk though about how we can actually generate these 3D elements and where are we getting these tetra elements from. And that's going to bring me back to the tetra mesh tool here. Now, there's one specific requirement for a tetra mesh, and that it needs to be an enclosed volume. So at a simple level, all solids are already an enclosed volume. That's great, but it's technically possible to tetra mesh an open volume that truly isn't solid. Think of like a CFD application where you want to model something as like a very thick air, or it's got a different density than the traditional air in the atmosphere, or you want to model something as a fluid, so it's not a solid, but I think you guys get the idea. This is an example of a part where this hasn't been defined as a solid, but it's more or less, for all intents and purposes, going to function as a solid. It's really just, it's a very technical and frankly pedantic definition in a geometry file. Now, it has to be an enclosed volume though, and that goes back to that idea of 2D surface topology we mentioned a little bit about Tuesday. I mentioned to you guys that topology is really just a way of describing how surfaces connect to one another at an edge. And in short, if you have surfaces that aren't correctly connected, you have a gap or a leak in your volume. And the tetra mesh tool does not like leaks. That's just one thing you can't jive with. So I'm going to actually, before I even start tetra meshing, I want to make sure that this thing is eligible to be tetra mesh. So what I'm going to do is, let me borrow my Spotlight tool. I'm going to come back to my quick edit menu in the geometry tool set. It's quick edit is how I can review topology, and it is one way we can think of it. And we see all these red lines, and these red lines are, again, were intentionally broken for the sake of this illustration model. I would not expect you guys to see this broken of CAD that you're coming up with. I used to joke that I designed intern level CAD when I was in our production design groups there, which frankly is not very respectful to interns nor anyone in a more of an amateur role there. But where I was going with that is I'd probably expect you guys to be better at CAD design than some of the customers I work with. I've had the luxury of working with both commercial users as well as design groups. Y'all kids are great at the CAD packages, so I really wouldn't expect many problems with it. That said, shit still happens. You might need to clean something up every now and then. We're going to remember that the toggle edge tool is going to be the home for stitching these surfaces. So the first thing I'm going to do is zoom in and identify I've got a little gap here that needs to be fixed. I could choose one of the edges with toggle edge and hope it happens. This was an instance where it didn't close the gap. The reason why, and hopefully you guys are knowing these answers before I get to them these days, is the tolerance in the tool was set too small. I was only instructing that line to smush together to another line if it found one within 1/1000th of a millimeter of it, which is pretty small there. I don't think we're on the nanometer scale yet. So I might bump this up to be, say, 0.1 millimeters or so, try to stitch that gap, still not working. So maybe I bump it up to 1, and that's when I can start to see it might get a little bit more friendly. Now, it also is click specific, I've noticed, on where you click. So it's sometimes better to try to smush these gaps by clicking on an edge where they're like physically closer to one another in a proximity sense. But now I should be good to just come in here. I've done this exercise enough to know I can just click many, many different red edges to smush them together. Again, try to click where they're already closest, like the bottom of those triangular splits. And a lot of this will fix itself. So what we're specifically doing is we're making sure that the surfaces at all of these red edges know they're connected and that there's not going to be a weak between them at those red edges. Because if there's any red edges left over, no matter how obvious, like a lot of these are, the tetra mesh tool won't work. And that's ultimately what we're about to be concerned with here is tetra meshing. So I think I got most of these here. I'm spinning it around. I'm doing good there. So what I'm going to do next is I feel good about it. Oh, we found one. Now this is a cool example for the quick edit menu. So that's a pretty big gap to close, right? I want to get this selected edge on the inside of the part to meet the other crescent C-shaped edge on the outside there, because that's a missing surface. But that's actually a really big gap to close across, and I would never recommend toggling edges or stitching those gaps bigger than about your element size, roughly, or anything bigger than that even. It has a tendency, toggle edge, to distort CAD geometry, so very, very small smushings is okay. Big smushes, not okay. It's going to really warp and literally almost like stretch your surfaces. They don't mesh cleanly anymore. It's kind of spooky. But right under the toggle edge tool, this is magnificent. There's a filler surface tool, and this thing is powerful. This thing is like the like 6th infinity stone, or I don't know how many there are. I think there's 5. How many fingers we have? 5. I'd assume there's 5 stones. There might be a 6th one. I don't know. We'll call this the 7th stone. Don't at me, MCU fans. But regardless, the filler surface tool does allow me to come here, select one of my 3 edges, and it will automatically detect that there's a chain or a completed loop of free edges. So essentially, if you have a loop of free edges, you've defined either a hole or a missing surface. We knew that this was a missing surface, so it automatically filled that chain in for me and tied everything together. So HyperMesh has some really cool stuff there where if you accidentally have just a really bad surface, you can always come in here to the quick edit menu, delete surfaces at the bottom, and you can come back in with a filler surface as needed to repair that geometry. Again, I don't think this is going to replace CATIA or SolidWorks in your toolkit, but it does save you the couple minutes of having to go, oh shit, I got to save this, export out a Parasolid, load that Parasolid into SolidWorks, redraw the surface, kick that out of SolidWorks, bring it back into HyperMesh, try again. How many words did I just say there? We don't want to do that. That sounds terrible. Let HyperMesh do a lot of the fixing for you in the environment it was designed for. So we're going to cross our fingers and hope I did a good enough job in cleaning up those leaks. And I'm going to come back to my TetraMesh tool. So again, I'm in the 3D menu. I'm at the TetraMesh column at the top of the column here. And what I'm going to do is set this to be TetraMesh, the default option. I'm going to choose a component to mesh here in a second, and I'm going to also choose where that's going to go. And rather actually than use TetraMesh here, excuse me, I misspoke. I'm going to use the volume Tetra option here. We'll talk about why. So it's asking me to choose an enclosed volume. I have a solid here, so I'm going to go click the solid. Nothing's happening. So I'm going to give it the benefit of the doubt and assume, well, maybe I just haven't classified this as a solid. I'll toggle it with this little arrow on the left to now change the entity to be surfaces. I'll go try to click the surface, but nothing's happening. If the volume Tetra tool isn't selecting your input, it isn't an enclosed volume. So the fact that nothing's happening right now, this is HyperMesh's very passive-aggressive way of telling me I don't have an enclosed volume. I'm not finished with my topology repair. So how the hell do I know where that missing edge is? Because as far as I'm concerned, when I look at this, I see green edges. And I'm not sure where that red edge is. And we might have found one here. There's got to be an easier way to find this. And what I can show you is a nice little trick that I've kind of picked up myself. I'm going to come over to what I call my visualization options. So it's typically hiding down at your bottom toolbar. It looks like it's a lone computer monitor next to the little favorites menu. And I'm going to open this visualization tool up. Now what happened is my model browser has been updated with all these different color settings. So what I like to do is actually uncheck HyperMesh from showing me all of my edge definitions except the free edge. So if we come back here, we'll see I've only checked the free edge, and I'm actually having it hide or not list all of my green shared edges. Now what I'm going to do is take my visualization method at the bottom here, and I'm going to set my geometry to be a wireframe geometry. So now the only things that are showing are red edges. So this is a really easy way to identify any missing free edges, and I've done this model enough to know they hide some really mean ones on you. Like on the inside corner of this part, yeah, that's the edge they have you toggle. I don't know the Altarian that made this exercise, but I have promised myself after dozens of this training class that when I discover who made this class, that one corner free edge that they leave in there, boy, that is mean. That is cruel stuff right there. So certainly if you're ever designing FEA exercises in the future, show some compassion, folks. And the final one I got in here, another one of those missing surfaces. Now we've talked about we don't want to smush those edges. That can cause some real ugly collapsing of the channel. What's better in this instance is a filler surface where it can automatically fill that in. Now one more time, I'm going to set that display to wireframe. I don't see any red edges, so I'll turn all of my other edges back on. And let's try that again. So what I can do is I can come into my 3D menu, TetraMesh, and I'm going to grab that volume Tetra tool. Now you'll notice when I grabbed a solid, it was able to select all of those surfaces or solids there. And now it's just a matter of a couple settings here. The TetraMesh tool that we're using here, remember, I'm using this volume Tetra tool. So a little bit of a comparison here. There's two ways we can even TetraMesh. So volume Tetra versus, I'll call it standard TetraMesh. What's the difference? Well, volume Tetra lets me go straight from CAD to 3D elements. Skip the 2D world, I'm all for it. Let's get excited, right? All for less work. Now the standard TetraMesh though requires an existing 2D surface mesh as input, and it will fill in the gaps or the empty space with 3D elements. So the pro to this, it gives me manual control on what my surface mesh looks like because I had to make the surface mesh, right? But the con that comes with that, I had to actually make the surface mesh. I don't want more work to do. Now, sometimes the reality is for me personally, I'm almost always making my own surface mesh. I'm just very comfortable with the surface meshing tools. I know for me personally, I can get a lot of the meshing I would need to be done in up to an hour, but it's okay for newer users if that's an all-day task, and that's just how the learning curve goes, and not every part's the same, you know. And I can tell you guys right now from my own experience, I've had meshes that, you know, should have only been 4 hours, but something went wrong and I didn't catch it right away or fix it the right way the first time, where there was a whole horror story that turned into an all-week thing. And sometimes I had things that I expected to be, you know, a 2-week meshing task with, you know, all sorts of different assemblies that only took me a day and a half. So it goes both ways. But certainly for newer users, I'm all for finding as many practical shortcuts, not just shortcuts for the sake of reducing time, but practical shortcuts to make our lives easier are something I'm interested in. And the fact that the volume Tetra tool just lets me go straight from CAD to 3D, a lot of good stuff with that. But like we're seeing here, I only have minimal control on how individual features get meshed. Otherwise, I'd have to go in and start getting a little more specific. Now, that said, you have still some control. I don't want to make it seem like volume Tetra is some like lottery of meshing quality where you gotta like really cross your fingers and, you know, like every 2 out of 7 tries only works out. It's nothing, certainly not the gamble that may seem it is. And actually, I'm going to steal our slideshow again to help me out with this, because there's 2 major controls you have in the volume Tetra tool. And those are a proximity control, which allows you to use smaller elements only at smaller features. So I know we've been preaching that we want to have as uniform element size as possible, and that's very true. But it's also practical to only use small elements when you have small features. And I would personally never recommend manually meshing with that in mind. You're always better off manually meshing with uniform elements in mind. But this is a nice automated tool where it can use some logic about introducing smaller elements at smaller features. And it's also smart about how it's transitioning back to that coarser element size. Because frankly, that's really the biggest concern I have with non-uniform element sizes, is a failure scenario where you have like a 20 millimeter gigantic element pulling on a series of many, many small 0.5 millimeter elements. That load transfer is not going to be smooth from the extremely large to the small element, and that's what I'd be weary of. Now this, HyperMesh has some smart things going on where, yes, there are smaller elements than others on the screen, but at least it's being good about how it's managing the transition from those regions. And even though this violates my big mantra from Monday and Tuesday, there's rhyme and reason to why I think this is not just acceptable, but there's benefits to it. And what this allows us to do is better capture things like fine curvature. So without that curvature setting you're seeing here, it's really kind of blocking and really just making an ugly looking hole. We're giving it the freedom to use the surface curvature. It's going to really capture that cylindrical feature that much better. So the volume Tetra tool has some controls in it, not a ton, but enough to get you going here. But certainly as your requirements get more strict and you feel more confident that you can get the mesh you're looking for, that's where the standard Tetra mesh procedure can come into play. So to wrap this little bit up here, because I do want to make sure we have plenty of time to talk about analysis, setup, and post-processing today, I'm going to just showcase those 2 workflows side by side. Excuse me there, I had a big sneeze. I didn't need the microphone to pick it up. Now, I said it before, the volume Tetra tool allows me to go straight from an enclosed volume. So now that I've cleaned up the topology and it's a weakless or airtight volume, it's selected the surface. I'm going to turn on those settings in there. I'll specify an average element size of 4 millimeters. I'll give it a minimum element size of 0.5 millimeter. And I'm going to let it know that I want it to make a surface mesh of trias and a 3D element of tetras. So very straightforward. And now we'll hit mesh. Excuse me, folks. So what came out of that, and again, you'll notice here in that same tool, we have that same where your element's going flag. So we'll place those in the same component as the geometry. And if I navigate over to my model browser, turn off the geometry, well, that's what we're seeing. I have, because I use the curvature and proximity settings, I have a very small series of elements. Now that's a little ugly. I'm going to come back and fix that myself here. Actually, Quality Index can fix that. This is a great example for this. So maybe you don't like this here. I don't want to remesh the whole thing. I'm going to use that 2D Well, I guess it's 3D, so it won't work. Nope, never mind. I got excited. I was wrong, folks. Ignore me. That's okay. But because we were using those proximity settings and the curvature controls, we're seeing a little bit of a mix here of a coarser element size to some of the larger planar features. And as it got more detailed at those small surface fillets, it was making a smaller mesh accordingly. Now, since I didn't mesh it myself, though, I can't really control for that flipped element there myself. And frankly, manually editing a 3D mesh is a disaster. And I would never recommend getting too detailed with a manual repair operation for a 3D. Because if I just use a simple mask operation to hide half my model, this is what it looks like on the inside. So just remember that internally, when you're moving one node, it's actually affecting like 12 elements that all intersect on the inside of that. So it looks very clean on the inside, but these tetra meshes are a bit of a jungle on the inside of all of these different shards and pyramids tying together to build up the volume. But it's actually that messiness, if you would, of all these jagged shards that actually makes it possible to tetra mesh every volume. Because for the most part, and I have yet to see something that can't be done this way, any volume can be filled with these shards in a very somewhat organized fashion. Now, it looks a little messy, but there's some rhyme and reason going on here too. And there's some controls you can apply to make sure you're getting, at least 3 elements in the thickness direction and things like that. But this is what allows it to just fill in any volumes. When I said earlier that any part is tetra mesh available, well, that's why, because mathematically, computers have figured out how to just fill in a volume with triangles for the last, this is as old as me, I'm sure, probably older than myself. Now, just to kind of give it an example here, I'm going to delete that mesh and go back to the parent geometry here, because I do want to take an example to showcase what happens if I actually have to make my own 2D surface mesh for it. So what I typically do for that is I'm going to use my same F12 menu we've seen. Hopefully you're noticing a trend here that 3D just builds off of 2D meshing. And I'm going to do the same thing. I can select surfaces. I can throw a mesh on there. I can come in here and adjust the element size. Now, right away, though, you're probably thinking, well, tetra elements were so triangle oriented. Why is he starting out with quads here? Why is he doing that mixed mesh? And you're 100% correct for thinking that. So the reason, and I've always explained it this way, one of the reasons we have different mesh types is because different 3D meshing operations have different inputs. So generally when you're tetra meshing, I would recommend meshing with a mesh type of exclusively triads. It just makes things a little bit easier. I know some commercial users I've worked with don't like the pyramid elements in all of their 3D meshes. They don't want to consider them. It's just not in their company practice for how they validated their CAE tools. So rather than introduce another thing that could possibly go wrong, they just stay away from the entity. Now, there's nothing inherently wrong with pyramid elements. That's just a very common thing I've noticed across different industries, is that for the most part, tetra meshing is done exclusively with triads. So I'm going to make an all triad mesh. And this still looks pretty clean. Now, one of the cool things you could do here is if you like planar regions, so take this rectangular surface here. Just inherent to the 60-degree triangle, it does not actually map to a boxy surface well, because the elements for a 60-degree triangle like to form this like radial flower hexagonal profile. What you can do to help map these kind of very boxy regions is use the right triangle meshing method, because the right triads, as we see here, map extremely well to a boxy region where they fit the boundary very cleanly. If we look at its neighbor mesh, they start to get a little squished at the end because they don't like to map to a box region there with the right triads. So it's okay to use a combination of right triangles and equilateral triangles. In fact, I use right triads, maybe not for something like that, but these cylindrical faces, I almost always mesh with right triads because that helps me get this very orthogonally mapped, almost quad-like pattern. So I'm going to actually clean those up myself very quickly here. And notice how HyperMesh just lets me take that existing surface and just mesh over it. And it's just going to rewrite it for me by default there. So I can actually take all those cylindrical faces real quick here, get those cleaned up with my right triads. Oh yeah, that looks a lot better. And if you look in here, I think they just look so much cleaner then if I went back and meshed that with the equilateral trias, which gives you these just really awkward curved surfaces. So really for cylindrical bodies, I would almost always recommend using the right tria method. Now, don't default to just taking everything. I'm sure some of you are like, I knew there was a caveat coming. At the same time, though, don't just default to always the right triangle, because right trias have a tendency to use more elements than they need to compared to their equilateral body. And the reason for that is they tend to map to a quad. So essentially, this is just a quad mesh that got split in half and doubled the element count. So there is a little bit of a sweet spot you want to find. And I think the easiest way to get to that sweet spot when you're tria meshing is to mesh with the equilateral triangles. And then as you need to, mostly at fillets and conical and cylindrical bodies, come into those individual features as needed. There's our lesson for the day, moderation. In moderation, let's only add those as needed, knowing they artificially increase the element count. So some nice things there. So what I have here is my surface mesh looks good. Just for illustration, I can take that same masking tool, got a little masking tool hiding all the way up here, and I can just select some elements, hide it. Now notice, this is hollow on the inside, which makes sense. I've only meshed the surfaces, but if we went through this, this is an airtight mesh. So it's all of these hollow spaces that HyperMesh is going to fill in with volume elements for me. Now, if I go back into my TetraMesh tool here, again, since I have a 2D mesh, I'm going to use the standard Tetra tool. And what you do is you select the component you want to mesh to. And then this is a very important trick here. Before I mesh, I make a new component. And I call this new component whatever the previous one was named that my 2D elements belong into. And I just call it 3D. So we had engine mount. I just made a new component called engine mount 3D. Why did I do that? Well, what's going to happen is HyperMesh is going to make all these 3D elements for me, but it will not delete the 2D elements. That might seem like a pain in the ass. It's actually a nice save yourself from yourself kind of feature, because in case something goes wrong with the 3D, you always have that 2D reference point to come back to. It's kind of like a checkpoint, if you would, in your workflow. And I want to make sure my 2D and my 3D are separate from one another, because we're going to learn in our next lesson with analysis setup that those tend to be, they can't be in the same component there. So I've just made sure that I have a new component. That new component, the 3D one, is set to be the active component. So now when I mesh this, notice how the 3D elements just went underneath the pink component, but they're their own color, they're in a separate component, and moving forward, it would be the 3D component that I would apply my properties and materials to, and I could probably just delete out that 2D. So it's a nice little workflow in setting that up there. Now, we got about 45 minutes here, so I'm not too much over my original schedule there. My goal is to get you guys out here by 5:30, though, and I'm probably going to stick around for a couple minutes after as well. But what I want to talk about next is the analysis setup. And this is where we define the physics of our problem and, frankly, make our mesh into something meaningful. So I preached it to you guys Monday and Tuesday that on its own, a mesh is fancy geometry that is essentially meaningless. It doesn't know how heavy it is yet. Those mesh elements don't know what material it is, how stiff something can be. They just know that they make up surfaces, and they are just one of many parts that make up the whole. Now, what we're going to learn in this next lesson, and I would highly recommend folks going through this lesson on their own if you have the time. If you go into your training materials in your student manual folder, I would highly recommend reviewing Chapter 7, Analysis Setup. It is a single exercise that I'm going to go through a little bit quicker, I think, than most of us would prefer. But the step-by-step complete every button click is included in this step guide. So don't worry too much about the individual clicks I'm going through. Let's try to make sure we're bringing home with us the theory concepts and the big picture with us. So when we have our own free time to dive into this and struggle through it at our own pace, we have a rough idea of where this is going. That's really what I want us to focus on for this example here, is making sure we can talk about it afterward and know what happened. So we're going to play a game where we all now work together at a big time submarine company. And a big-time submarine company, we make just that, big-time submarines. And we got a mini competition going around the office where we're Team A, and we're going to go beat up on Team X to come up with the submarine design that can keep all of us alive at a depth of 1,000 meters below sea level. So we want to make sure we're designing a vessel that is strong enough to be able to survive those depth pressures at 1,000 meters under the sea, or however deep we want to go. Team X sucks. They've only made it 50 meters down before their vessel did not make it. Fortunately, no one was in that vessel. We're currently making fun of their prototype, which didn't make it. And we got to stick it to Team X and show that we can make a worthwhile submarine that could survive those depth pressures. So what exercise 7 has given us is just one of many of those submarine panels. And we're going to kind of be clever about how we're setting up the physics of the part to account for both symmetry in the design, as well as the fact that there's certainly more submarine here than being modeled in. And we're going to kind of, it's a very good lesson to show you that FEA allows us to absolutely work smarter and not harder. And that's hopefully what I think we should be taking from this. So this is one of our many submarine panels. Of course, there would be more of these above it and to the right of it and to the left of it and underneath it. And this would enclose a volume. This is just one of many panels and the ribs here included. What we need to do is make a checklist of all the things that we're going to have to define here. So in your analysis setup, this is really what's responsible for defining both the physics of your problem and giving your mesh a physical meaning. So we're going to need the following things. We're going to need a material and its kind of partner entity, a property, to define model stiffness and weight, right? Those are those two entities that go hand in hand. We're always going to think of them in pairs to actually give a physical meaning to the mesh file. But on top of that, I need to know a load as well as a constraint scheme or a boundary condition, as they're often called, to define the physics that we want to model, right? Like, we don't want to just make a really good submarine drawing. We want to be able to stick it to Team X and say, for a very matter of fact, in your face kind of way, that I know this part can survive depth of 1,000 meters under the sea there. And we do that by setting up loads and constraints which resemble the load cases that our parts would experience in the real world. So we're going to do a couple things here. We're going to learn a little bit about materials and properties and how those give our mesh life. And we're also going to learn how we can start defining physics in our models. And this is really the expertise there. Now, what I like about this is it's a little bit separate from meshing. Now, definitely we're going to be interacting with elements, but this is like almost a different step in the workflow than the meshing is. And what I like about that is they've given us the mesh to work with, so we can put our meshing brains on hold for a bit and let them take a rest. But whether it's a part that took 3 weeks to mesh over 6 users or something that you yourself put together in 20 minutes like the submarine hull, the steps are generally going to be the same and the requirements are the same. So analysis setup is relatively straightforward in my mind. So how I like to do this here, if I look at my model browser, I just truly only have one component at the moment. We're going to need to create a few new entities. How I like to do this is I prefer to right-click the model browser space. The top option for that right-click menu is Create, and I can create essentially any entity HyperMesh supports from this window. I'm going to choose from that list a material. I'm going to repeat that to right-click, create a new property, and I'm also going to right-click, create a load collector, and there's going to be one more. I'm going to right-click, create a load step. So let me come back to my checklist here. So we need some new entities. We needed a straightforward, we needed a material, we needed a property. I think those are pretty obvious, and we'll talk a little bit more in detail to them if you're not sure what exactly they do. But we also have our loads, a load collector, which is really, it's just a component for analytical entities. You know, you don't have a CAD file for your point force. You don't draw up a pressure load in CATIA and import that into HyperMesh. Of course not, right? That isn't a geometric entity. It's a force. It's a pressure. It's an analytical entity describing the physics of the part. But still, it needs to live somewhere. right? Like our geometry files or the brackets we're importing in, they live in a component. I like to think of components as a house for elements and geometry. So you've got a whole neighborhood known as your model. You got individual houses we refer to as components. Well, just like our elements and geometry needed a place to stay at night, our forces and boundary conditions and moments and pressures and gravity definitions, they have to live somewhere still, right? We don't want a bunch of homeless people on our model. That'd be awful. So that's the idea of a load collector. It's an organizational entity which houses our analytical entities. So all of our loads, our constraints which hold the model down, pressures, anything like that is saved as a load collector as the entity, which is why we needed those. And the fourth entity we went ahead and created there was a load step. And this is really just a way to organize and pair up different load collectors. So really, we're going to see this in a moment here, but the idea of a load step, it might seem redundant at first because you've already defined a pressure, you've already defined a constraint. How does it not have enough information to solve? The idea behind a load step is if you want to have 3 different loading conditions, right? So if I come back to my submarine model, you know, maybe no matter what, we're always going to fix the exterior nodes of the model. But maybe we want to consider a situation where we push with 100 newtons on one edge, but then the next simulation is 250 newtons. It's nice to be able to reference different load collectors in a load step so that way you don't have to keep repeating the constraint definition. I'll show you what I mean by that with this example. So what I need to do with this example here is I need to first define the materials and properties. So these are 2D elements. So they're going to use what we call a shell property. And before I go too far, do yourself a favor and come into your preferences menu if you have software up or if you're doing this later. Make sure under the user profile setting, you may have seen this dialog pop up. For this exercise especially, you want to make sure you're using the OptiStruct user profile. The analysis entities that we create in HyperMesh are directly dependent on the solver profile we're using. That might seem funky, but it's a good idea. What it really prevents is you having an abacus model with HyperMesh, or not HyperMesh. You don't want an abacus model with OptiStruct loads in it, or a RADIOSS model with LS-DYNA material definitions in it, right? All of those different products, whether it's ours or another competitor's software, they all have unique formulas and file formats they support. You want to make sure the entities you're creating are going to be read in correctly to that solving technology. So that's the idea behind a user profile here. It's essentially a giant filter that hides away unsupported entities from the solver you know you're going to be using. So with that said, I want to make sure I'm in OptiStruct, since that's how I'm going to solve the job. So I need to first define my material here. And I promise you I will share this note sheet with everyone here in a second here. Material needs 3 fields. It needs E, new, and row. Because those materials, or those 3 fields, define the following things. Those give me stiffness, how it deforms in the form of a Poisson ratio, right? It lets me know how an element can deflect, and the density gives me the part mass, or the weight of it there. So I know from just those 3 fields in a linear material, a Young's modulus, a Poisson's ratio, and a density value can tell me how stiff something is, can describe how those elements can deform as they're loaded, as well as tell me how heavy the part is as a whole. So when I said a mesh doesn't know shit on its own, that's what I meant. The mesh didn't know how stiff it was, how it's going to deform, how heavy it is. It needs a material definition to apply the scalar numerical values to it in order to actually have those physical properties. So that's the idea behind a material. Now the property card is what's going to be responsible for turning a 2D element into a 3D object or volume or solid, however you want to think of it. Because right now I have paper thin elements, and I'd almost be willing to guarantee you a big time submarine company, not a single one of us would get in a submarine that is truly paper thin, no matter what it was made out of, right? That is a ridiculous concept there. So of course we're not modeling this in as paper thin. And in fact, the exercise will let us know that the ribs are supposed to be some like 11 millimeters thick, and the hull itself on the exterior is supposed to be 19 millimeters thick. So I'm going to have to rely on a property card in order to turn those 2D elements into a 3D object. So let's see that in action here. So I'm going to come to my property down here, and I'm actually going to rename this to be, one of my properties is going to be renamed for the exterior hull. So property 1 is hull. and I can either right-click property and create a new one. You can do that same right-click menu and access a new one, or you can come up to properties, create new. There's a bajillion ways to do this. And we're going to call this next one ribs. So what I want to point out to us is for 2D elements. For 2D elements that you want to make into 3D elements, you use the P-shell card image. Card image is a flavor or a variety of property. As you get more familiar with OptiStruct or other SE tools, you're going to learn that there are dozens. It is a nearly endless list of all sorts of properties. We have properties to describe springs, properties to describe beams, to describe bars. Not the bar you're thinking of. I know it's Thursday. We're not there yet, folks. But we have all sorts of these different property cards that give these meshes life, that really bring them in to value there. So the first one that defaults to, fortunately, is the P-shell property card or the 2D card. And also the property needs is first it ties to a material definition. So I'll click that material field a few times to tie my soon-to-be defined material to it. And the only other field it needs is P for thickness. And that is an 11 millimeter thick rib. That's my rib property. So again, if I come back to my checklist here, so we learned that I have P shell for 2D elements, and that just needs material and thickness just need to be defined. Now, the other property, I'm sure some of you thinking, well, so we can't use P shell, it sounds like, for your tetra elements. And that's 100% the case. What we use instead is a card image called P-solid for 3D elements. And P-solid is almost redundant. You literally only need to define a material by default. There's a couple other flags in there for working with like non-isotropic materials. If you want to kind of have the part be non-uniform in that sense, there's some ways you can manage that. But P-solid, it just needs a material definition to it. So how, again, this actually turns a 2D element into 3D here. We're going to play one final game of Pictionary together, folks. I know I'm hearing all the groans in my head. Now, consider I got a flat sheet of paper here. We'll do a top-down view and a side view. Very fancy. What I'm going to do here is this actually volumizes by adding thickness to the top and bottom of the part. Hey, this didn't turn out too bad. So what it actually does here is it applies half the thickness on top, half the thickness on the bottom, and that's how it turns an infinitely thin piece of paper into a cube. So up here on the top, I have, this is T over 2, and over here, we have another T over 2 as well. So that was that idea of a mid-surface. But simply put, it takes that thickness value you have in the property, divides it by 2, makes that top and bottom. Now you have a volume, and simply put, the volume with the material definition can turn that into an element there. So that's where that stiffness definition is being derived from. So I have one property for my ribs, which has a thickness of 11 millimeters. I have a second property that I'm going to, again, tie that material to. Now, this thickness will be 19 millimeters. It's very important you understand that for every unique thickness you have of shell elements in your model, you're generally going to need a unique property for it. So in this model, I had 2 different gauges to work with, an 11 millimeter and a 19 millimeter thick sheets of metal. I needed 2 properties to account for those. Likewise, I'm going to need to organize my model into 2 components, so that way all of these elements on the screen here can be organized by property. So even though this is one submarine hull, and we had meshed it accordingly as one component, and it probably came in as geometry if I had it as a single body, it's okay to take one part and break it up into 5 different mesh bodies, as long as they're all connected together. Or sometimes you'll have 5 different parts get turned into one component or one single mesh body. There's various reasons, and both can be valid if you can justify it and find a good use for it. And this is an example where we're going to turn one part into 2 components, so that way we can correctly define the thickness. So what I'm going to next do here is come up to my component header, right-click it, and create a new one. And I'm going to call this guy, you can call it either one, ribs or hull, or leave it blank there. So now I have 2 components, though. And I'm actually going to arrange these by all of the elements that will be the 19mm thick exterior hull and the rest of the elements that make up the 11mm ribs, and there will be no overlap, and we're going to draw a clear line in the sand where our components are going to differ. But how the hell do I actually move these now, though? What do? I don't have surfaces to mesh. Is there a move key? And what we have is even better than a move key. And again, y'all are probably laughing at me. The best tools of this product are by far the least sexy and memorable tools. But there's something called Organize, and Organize is a revelation. And I promise you, anyone who has done FE work, if you haven't had a similar tool in the products or weren't aware of it, it's a game changer. Because what Organize allows me to do, and again, this is on that bottom toolbar. It looks like a manila folder with like a red arrow going from one or the other. What Organize allows me to do is take any element or frankly any entity in my model browser and move it from component or collector to a different component or collector. So I mentioned I like to think of my components and load collectors as houses. Well, if you need to move an entity like an individual load or a group of elements from one house to the other, because maybe you forgot to change your current component when you're meshing, or we forgot that we were going to have different sheet metal thicknesses down the road here, you can always move things using Organize. So what I'm going to do here is I'm going to select all of my elements from on the ribs here and move those into the destination component labeled ribs. So how can I do this? Well, first off, I'm going to do myself a favor and turn the geometry on. So I know it's tough to see here, but if I turn the elements off for a moment, I do have surfaces here. And what I have here are all these different faces, right? But I can even make that even easier for me to work with. And I'm going to do that with some selection shortcuts. So how I'm going to do this here is I'm going to select one element on this ribbed face here at the top, maybe grab its neighbor next to it, and I'll do the same thing on the opposite side, just select two of these elements. And I'm just going to do this for more or less every unique geometric face. So I'll come into this side, just grab two there, grab two here. And you don't have to do the back side, of course, because it's the same element. They're flat. But if I do this a couple different times, and you can do this the other approach as well here, I'll talk about that in a second. So I just make sure to come grab all these faces the right way. And again, I'm not clicking everything. I just need one on a face. I'll show you why in a moment here. We're going to do some voodoo magic. Or I suppose magic. I don't want to specify. All magic is good magic. Now, what I'm going to do next here is I have all these faces sort of selected, right? But I don't want to go through and click 300 elements. I'm going to get carpal tunnel and be learned yesterday. I'm going to yell at you if you do that. So now that I've pre-selected some of those faces, I'll click the yellow elements panel. And there's a shortcut option down here called by face that will allow me to select elements by a face. So now you'll see that all of the elements I already had selected, it just went ahead and grabbed all of the remaining elements on their face to my selection. So there might be a few in here I still got to come back and grab individually. I'm okay with that. But that saved me a heck of a lot of clicking there. Now I'll come back for those separately, but once you have it selected, you can choose the destination component and move those elements to it accordingly. So I'm just going to come in here and wrap that up. And now what I'm left with, hopefully, as I kind of speed this up here, of course, I've seen people do it the other way where they've selected the exterior of the hull and moved those to a different component. Either works. As long as we get the end goal the same of I need my ribs in a different component from my exterior hull elements there. That's the only thing that matters, and that's what we have here. So I think the exercise, if you do the step-by-steps, will have you take like a patch of all those elements this way, just kind of approximating it, do elements by face, and that's a way you could grab the exterior out. Tomato, tomato, if you want to do remove A from B, remove B from A, more power to you. Might be a good idea to figure out how to do both and get comfortable with it. Now, either way, though, I want to come back and iterate why we did this step, and that's because of how we actually apply properties to our components. So coming in here, I'm going to take this middle surface component. This is my exterior hull, so I'm going to rename it. And we're going to call this outer hull. And now what I'm going to do is in that little entity editor, the window under my model browser, I can see that I have outer hull selected. It's component number 16. It's colored orange. I have a property I can assign to it. So this is where I'm going to click that unspecified property, click the yellow panel, And I'm actually going to call out that whole property we've already defined. Notice the material definition follows suit with it. So it's a nice little system where the material feeds into the property feeds into the component, and now every element within this component is going to receive that material definition, kind of like a big water slide. Let's do the same thing for the rib, right? I have a rib that needs a property. I'll point out the shell property. So now it knows that these elements have some thickness and that it's that same material there. So now what I still need to do, though, is define that material. I mentioned before that we're going to only define Young's modulus, nu, and rho. HyperMesh defaults to a unit system of megapascals for pressures, millimeters for length, typically, seconds for time, newtons for forces, and here's the real kicker, the megagram for mass. So the megagram is in there just to make sure that you're still getting pressures in megapascals. So that's why they use this funky system here, millimeter second Newton megagram, because it's easier to work with megapascals than pascals or something else. But we're going to try to remember that default unit system. And again, I will share this with you guys before we leave today, this little PDF I'm making here. So knowing that that's our unit system, that's really what's going to be deriving all of our units moving forward. And I typically build my unit scheme in the material definition. And frankly, to make this as easy as possible, as long as you define your material with the Young's modulus in terms of megapascals and a mass in terms of megagrams over millimeters cubed, you're going to get the right values out of your software. So what I'm going to do is come into my material and I'm going to rename it to be steel. So to make things even easier, the default MAT1 material definition is steel in the above unit system. So if you're ever really confused about units, and I don't blame you, that was probably the hardest part for me when I learned FEA. What I'd recommend doing is come into your favorite search engine. Won't tell you which one you got to use, but just look up, with things like FEA unit systems. And there's all sorts of third-party literature, and it's not my place to sit here and recommend, but I had actually this exact chart here. It's so funny you can pull this up still. I remember this from like 8 years ago when I was first getting into this. They have this little chart here that actually shows you the same steel material and unit definition in like 12 different unit schemes. So if you're ever confused on what value you need to be working with in a different scheme, they have a sample material that's just redefined like 10 different times for all these different schemes to help keep it clear. So I used to have that taped up over my little desk at my research job, and that helped me get through things. What I would do if I were you guys a little bit easier is just know that these default values that it recommends when you come to any of these fields, I didn't type in that 210,000. That's 210,000 megapascals of Young's modulus, which we know is the stiffness of steel. So it's actually always going to give you the default value for a steel material. And if you're wondering why the density is at an e to the -9, just remember this is in megagrams over, millimeters. So it's going to get all super messed up with all sorts of zeros in the way there. So got my steel material defined. So the final things we need to do, if I come back to my checklist, well, we've done a really good job of giving our mesh life now, but we have no idea to prove to Team X and our submarine, even though we got it physically modeled in now, how the heck can I show them that this is going to survive pressure depths, right? So what I'm going to do is I'm going to come in here and we're going to reference our load collectors now, the components for analysis entities. And like the pairings of materials and properties, there is a partnership we're going to learn about. And those are loads, and I'm going to use a pressure in this case, and they're twin boundary conditions or constraints. I think it's pretty evident why we need a load. In this case, we want to see a pressure load because that's what we're going to make sure the part can survive, right? That's the environment it's going to be in. If you're designing an auto part, it makes sense to, have steering loads in there to make sure the car can turn correctly in your suspension system. But why do we need a boundary condition? And the easiest way to think of it is going back to Newton's laws, right? An object at rest won't move until it's accelerated, and an object that's moving won't stop moving until it's decelerated, right? So in essence, if we don't provide something that's going to hold down my part in space, if I just load a part, it'll fly off to infinity because we didn't take the time to model any friction or drag forces that would slow that down, and there's nothing tying it down elsewhere, and that part never stressed, right? Because stress is only formed by the fact that there's something holding it down or there's a constraint applied to that deflection there, whether it's the fact that there's other material tied to it, whatever it could be. So we need constraints to actually allow stresses to form, and we don't want our part just flying off to infinity there. So that's what we're going to do here. And now I told you guys before, we're going to kind of do a cheat code here, and we're going to see how we can be clever about our constraint scheme to model the fact that there's more submarine hull included in this model. So how can I do that? Well, first off, I'm going to make my pressures my active collector, the current collector. So again, notice how I right-click the pressure load, and I'm going to make this current. So the first thing I'm going to do is define my pressures to get that out of the way. And I like my pressures to be purple. The first gentleman I worked with at Altair had a extremely picky model requirement where my constraints had to always be yellow, my forces were red, pressures were purple. There was all sorts of this ridiculous color scheme, and I don't know why I haven't got out of yellow constraints and purple pressures though. It has stuck with me till the day I forget. So what I can do is I'm going to create a pressure load, right? And you guys are going to love this, and I'm sure you saw this coming. All of our analysis entities are created from the analysis menu. And really the one we're most concerned with is this column towards the left, the second column on the left, has our constraints, forces, moments, and pressures, kind of our most common entities we work with. So I'm working with pressures right now, so I'll come in here, and I'm a little confused because I don't see a yellow panel. Well, this is just a shortcut of saying it is a face of elements. It's just defaulted to be not one element, but instead the entire face. So I'm going to come here and I'm going to select these orange faces that I don't like how they built this mesh. It's a little jagged. You got the occasional lone element isolated from the group. That's okay. I got everything on the exterior modeled in. Now what I'm going to do is apply a -5 because I want it to be a compressive pressure, and we'll confirm this is the case, a -5 megapascal pressure, because maybe that's what we experienced at the depths we decided. I have no idea about nautical pressures. You guys could be laughing at me because I'm totally off in magnitude. Please be gentle. I have never been underwater that far, and I'd be shocked if you have been too, so I don't want to hear anything about it. But that said, I can throw in my -5 millimeter load, or excuse me, megapascal load. It's defaulting to the element normal, which is ideal. And now the only other settings in the tool here are graphic settings. This is just describing how big the arrows are going to be in a moment, and the face angle is just a limit selector on how many elements it was grabbing. And P load 4 is the preferred pressure load that we work with. So I'll hit create. I'm having a hard time seeing something happen. So I'm going to take this relative size, toggle it to uniform size, and I'll change that to 100. And now we'll see my arrows grow. And if I zoom in, I can see that the pressures are being applied compressively onto my structure. So those are pointed the right way. So we used a negative pressure. That was good. But now we got to fix this thing in space. We need to model the fact that A, the submarine hull exists in our universe that does have, forces that will prevent it from just accelerating into infinity. But we also want to be smart about that and also model the fact that there's probably some symmetry on the components. So I'll do the simple way first to kind of warm us up to this here. So first here, it's very important when you're working with these that you take the time. You have to do this, and things will get broken otherwise. Before I define my constraint, I'm going to select the constraint collector or house. I'll right-click it and I'll make it current. This ensures that the new constraints we're about to define end up in the right house. HyperMesh is like the pickiest eater at Thanksgiving. It doesn't like its mashed potatoes touching its turkey, touching its stuffing. It likes things very separate based on the entity it is. So in short, pressures and constraints, they go together, but they don't like to live together kind of thing, right? They got a good carpool thing, but once 5:30 hits and they're home for the day, they stay in their own home. So likewise, I have my constraints organized accordingly in their own component. And like we saw, if we ever screw that up, that organize tool we saw earlier can move more than just elements. It can also move loads. And anything we create in the analysis menu, a constraint, a pressure, a force, is classified as a load. So you can always move loads as needed between load collectors as well. But either way, we were smart about setting our boundary condition as the current collector. I'll come back into my analysis menu, and I'm going to pull this constraint tool. The constraint tool is very straightforward. you choose nodes which you want to constrain. And this will enforce a zero displacement at these nodes essentially. So I'm going to choose a shortcut here where I'm going to do nodes by path, hiding all the way at the right side of my shortcut menu. And again, I got to that shortcut menu by clicking the yellow panel. Node by path allows me to click a few times. And now what I can do is I can click away from my selection and it'll automatically select all of the nodes that make up the shortest path to get from node A to B. So this makes it very easy to select all of these exterior nodes. I don't have to click some couple hundred times. I just need to click a dozen times or so. And just like that, I was able to very quickly select all of those nodes for a constraint. Now, the only other thing I need to do here is define how exactly is this constraint restricting motion. So the constraint I'm seeing here currently has all 6 degree of freedoms turned on. In short, degree of freedoms 1, 2, and 3 are translational degree of freedoms. Movement in X, movement in Y, movement in Z, right? Can it move back and forth in that vector direction? 4, 5, and 6 are rotational. Can something spin about the X-axis? Can it rotate that way? Can it rotate about the Y-axis? So really, what this means on the screen here is I've agreed to check on or control for movement in these 6 degree of freedoms, 3 translational, 3 rotational directions. And now that I've agreed to control for those, how much do I want to allow it to move? By setting these equal to 0, that's saying, yes, I want to control how those nodes move in X, and I want them to move exactly 0 millimeters. That's what we've set up here there. It's not a true enforcement. It's an allowable limit is a better way to think of it. But for the most part, your most common constraint scheme would be constraining all 6 degree of freedoms and apply the constraint there. Those will simply restrict motion. Now, if you're going through this exercise, I think that's a really good way to do this to start, is just constrain all 6 of those nodes. But you can also be clever with your constraint definition to imply additional components or symmetry in the part. So what I'm going to do here is demonstrate that to a very quick degree here with this edge on the top of my screen. So let me put this in a global view here. This is a good view. So I have an edge of nodes up here, and I'm going to just grab them with a window selection here. But we know that this is just one of many holes in the part. There's definitely more submarine hole that continues in this positive Z direction up the screen. So to model the fact that there's probably more submarine hull above me in the Z direction, but probably not submarine hull to the left and the right of me in the X direction or in the Y plane in and out of the page, what I could do is constrain this element from moving in that Z direction, as well as constraining rotation about X and Y, because those technically contain a translation in Z movement. And now what this degree of freedom setting is saying is, these can move a little bit in X and Y because there isn't material stopping it there, but there is something not modeled in here in Z that would prevent this from moving up. So I might model those nodes at that edge, only constraining in the kind of Z directions. Likewise, I could take my edge on the side here and only model this to be constraining it in the X direction or where my other hole might be at the side of it. I could do that same thing for the right side of the part. Let me just flip it around though for myself. Take all these edge nodes down here, same thing, move those in X. Then the only other thing we need to do now is to take this bottom edge of nodes, and this one is going to prevent movement in the Y direction. I don't expect you guys to become experts in that idea right away, but the biggest thing to try to remember when you're reading through this exercise, if you have a chance to go through it, is those degree of freedom definitions were defined very specifically with the idea that there's an imaginary panel we didn't take the time to mesh included in there. And that's why we're constraining them as such. If you're really confused and struggling to get your head around that, I don't blame you. It's not an intuitive thing. You can always constrain it with all 6 degree of freedoms, and it's more or less the same thing. So the final thing I need to do now is define a load step, because this will pair together my load collectors and conditions. So I have a load step entity I've created. I'm going to come in here under analysis type and update this to be a linear static analysis. Linear statics are our basics of FEA. And the only 2 fields I need to supply are an SPC and a load. So I'll add that in here. So we're doing a linear static load step. and it just needs an SPC load collector and a load collector. So pressures, moments, whatever. So what this is asking me is locate a load collector with a bunch of constraints or SPCs in it. Well, we got constraints. This field for load is asking me what are the loading entities, why a pressure is defined. That's it. We're good to go. So the final steps here, if I come into my analysis menu again, the bottom corner option is called OptiStruct. I can click OptiStruct. I could save the model somewhere else if I wanted to. And I would recommend getting in the habit of saving your model in a new folder, just because all of the run files and the result files we're going to get in a moment here are going to be all saved in that location. And it just really makes it easier to have all of your files saved in one spot. Once you submit your job to run, it's going to immediately prompt the OptiStruct menu that's going to pull up on the screen. And the message log is where it's going to let us know how things go. So any errors, you forgot to apply a property to a component, it didn't know how stiff the elements were, it errored out immediately. They'll generally tell you in the message log. So some common things I'll see from newer users in my classes could be you forgot to apply a material to a property, or you forgot to apply the property to a component. Sometimes people forget to adjust the current load collector, so both their pressures and constraints live in one collector and the other is empty. As a result of that, when it reads the subcase, it finds constraints and pressures in one field, but none of those in the other. HyperMesh doesn't want to make any assumptions for you, so it's just going to error out there. Now, if all goes to plan, you'll get the analysis completed menu, and this is when all of your hard work's paid off. You can click your results button, and right away for you, it's going to prompt up your model in HyperView. Now, I'm sure some of you are thinking, man, he gave us 7 minutes before the scheduled end of class to talk about post-processing, but I promise you, if you've taken the time to diligently build your model, you used a little bit of common sense when you're going through it to build it, HyperView is the easy part. And I'm getting in a little bit of a fight with my application. It's not letting me minimize it. There we go. Now I can bring it over. I've automatically launched from that results button. It brings up your model in HyperView. Now this is a separate application, but there's a lot of similarities between HyperMesh. And there's a lot of things you can do with it, but what we're concerned with for probably 90% of our applications is only a couple clicks away. So from a visual standpoint, we do have all of the import, export, those model view options. A lot of what we saw in HyperMesh is still here. The biggest thing that changed is your panel area is going to be a little different now. And this bottom toolbar is no longer all of the rendering tools. There's a lot of post-processing tools we're going to pull from this bottom. So what I like to do when I post-process is first turn my mesh lines on. This, we'll talk about why in a moment. And then what I do is I come over to my contour tool right here. It's a little bit of a rainbow flag. The rainbow flag is what's actually going to apply your results onto your mesh. So here I can actually choose from different result types. So we have displacements, but I can also drag this open to see I have stress results available. It'll automatically select all of your components for you, and I can just hit apply in the tool to turn that on. So now what I'm seeing is a scheme where blue is low stress, red is high stress. I have a legend that came up on the screen. Now, some things I like to do when I'm post-processing or reviewing these results is I'm going to edit my legend in this little legend tool set here. So I can open a legend tab, hit edit legend, and this little micro dialog comes up for me. I typically remove the scientific notation to a fixed format with maybe only 1 decimal point of precision. Some other things I like to do, you can also adjust your color definitions on these as well there. So I'll take off my lowest color. Instead of that deep blue, I might set it to gray, just so that way my low stress regions are just a deep sea of blue staring back at me. And another thing you can do is maybe you have a yield stress in mind, right? So maybe that whatever material we use for our submarine here yields at 320 megapascals. I'm not a big materials guy, please don't make fun of me, but off the top of my head, I couldn't tell you what steel yields at. I'm gonna go with 320 megapascals. And we wanna make sure that our submarine isn't gonna experience any stresses at or near 320, right? Because we don't want to see this thing explode when we're down there. We gotta really stick it to Tmax. So to help me decide where all of the elements are above 320 megapascals, I do a 2-step process. The first of those being I apply an averaging method to my stress results. Right now, we're seeing one element, one result, which is preferable, right? That makes sense to us. We were just talking all about these shape functions the last couple of days in Hooke's law, and damn right I better get a result for every element. But you can also apply an averaging method like the simple average, which allows you to blur the lines of your elements. So now what I'm seeing are stress results that are accounting for the effects of neighboring nodes and elements at each element, and my contour can blend through the mesh lines a little bit. In general, simple averaging methods are the preferred way and the most common way I've seen from my commercial customers in using stress results. The reason for it is it gets away from being an extremely mesh dependent result. You're allowing the physics to speak up a little bit more compared to the raw mesh that you had. So it's taking a little bit of influence away from you and giving the physics of the part a little bit more influence on the result. But it also lets you kind of confirm the effects of a bad mesh. So what I mean by that is I have with a no averaging method here, I have a bright red element flaring up here. I don't know if that's flaring up because it's got a rib tied to it, if it has the boundary condition applied to it, or if the mesh was so poor that it's artificially inflating the stress values it's seeing. Now, I feel pretty good looking at this mesh that it's probably not geometry specific, but the averaging methods can help you ensure that, because what I see from here is, while the whole element isn't failing, it's really just those couple nodes from the rib in the exterior of the part that are flaring up. And that makes sense to me intuitively, that there's a lot going on there. That's a boundary of the part as load is transferring outward into the ribs. It's kind of getting stuck at that edge there. And that's why we're seeing a peak flare up there. So some cool things. But that didn't necessarily help me determine where everything else is that could be over yield. So what I like to do is I'll come into my legend, and you can actually click on these threshold values. So HyperMesh will automatically assign the red color to be your maximum stress and vice versa. They are equidistant to colors. But I can also just select my second to last color, the one that describes the threshold between the orange and the red, the default rainbow, and I'll set that to be 320 megapascals. I'm going to hit apply. So what I've done there is everything over red is now going to be at yield stress. So again, I kind of just made up some values. 5 megapascals is probably too big of a pressure. But we're looking at this, and what we could take away from this is, you know what? Maybe we're not going to get in that submarine together. We have stresses as high as 612 megapascals. An overwhelming majority of this part is yielding at that stress. Maybe we need to go back and either add some different ribs, experiment with different property thicknesses to beef up the part, or something else has to happen for this to yield. But right away, we were able to make those judgments. And what I hope we're seeing is, because this mesh is so clean and so wonderful, I didn't have to worry about that mesh. Whereas if I come back into my part file, and what I'm going to do here is really screw some of this up. Maybe too much. I'm going to save this guy now and resubmit just this job here, and that's the one we're going to come back to in a second here, to show the effect of that. Now, while that's kind of running in the background here to show us how a bad mesh can sometimes affect results, I want to show you a few of the other basic and very quick things you guys can do with HyperView. There's a lot of kind of stuff in here. Now, what I'm going to do is just reset my legend back to the default settings for a moment here. Some of the other things I like to do are, next to the contour tool, we do have an ISO contour tool here. The ISO contour allows me to kind of literally, again, throw things like my stress contours on, maybe apply those averaging methods, but I can literally hide elements with this slider bar based on those contour values. So it's a very easy way to find all of your regions over a certain threshold, or if you want to find things less than a certain stress, you can certainly adjust the logic to be above that threshold as well. And there's some cool little visualization controls in here that you can manage, like the features or applying a transparency to it while you're cycling through your ISO contour. So again, this is the ISO contour tool. It's right next to the standard contour tool. Works very much the same way, just gives you a little bit more freedom on what you're hiding, what you're not hiding there. And you can always clear that right from here as well. Now, another common thing I'll see from my users want to do is call out a specific measurement, right? So maybe there was an area of interest that we wanted to track the exact yield stresses at. What I would do for those is work with our measure tool here. So it kind of looks like a bar next to the little quotation with an X and a measure icon. This tool allows me to come in here, and first off, for any given contour, it can call out the min and max locations for me. Again, I know it's a little tough to see on the screen. Let me try to blow up the font for you. But I can have it label for me on the screen, you know, where those high stress regions are. You can change the color of them, manipulate the fonts. So again, that's the measure tool down here. It has all of these different min and maxes that it'll default to for any given contour. So to kind of illustrate that, I have my stress contour up, but if I switch it over to displacement, you'll notice the min and maxes got moved from it. Oh, I don't have any deflection results. Oopsie. Oh, I know what happened. I just saved all the results, so I can't reference those anymore there. So what I'm going to do is let's load in the new results there, since I broke it anyways. So again, this is that same model, though, if I just call one thing out here very quickly, and I appreciate everyone's patience. I'm only going to keep you for 5 more minutes. I will not be offended if you have to run out here, though. But I do appreciate you guys taking the willingness to stay over with me for a second here. So this is that mesh that I intentionally screwed up here. And what I wanted to show, so if I just bring up those stress results, this one is now artificially adding stress to the model, right? We're seeing how it used to be relatively lower stress. So the shape of this element is causing that stress to flare up a little bit. But what I like is when I apply the averaging method, it actually shows that it's still really only that node from up here that's the case. So yes, this is a nice example to show how individual element shape can locally distort results. But at the same time, the averaging method in post-processing helps take away that influence a little bit to kind of balance it out. We really don't want meshing to be a volatile practice. And in post-processing, those averaging methods can really help minimize that volatility of it. Now, we've seen some basics of measuring, we've seen some basics of contouring, but the real kind of final thing we haven't seen yet is, of course, animations as well there. So HyperView does allow me to play an animation of it. Now, you're probably thinking to yourself, well, nothing's happening. So one thing you can do to help with that is there's a little a tool here that's got another one of those bars with a red arrow on it. It's called the Deformed Shape tool. What this allows you to do is apply a scale factor, something like 25:1, to exaggerate the animation. So I know it's tough to see on the screen sharing. I don't know if the frame rates come in super cleanly or not over the webinar. But now hopefully you're able to see the part that is showing that contraction from the compressive loads. Is it literally shrinking, 10%? No, but we're exaggerating it just to help us be clear on the model behavior. I could also amplify that to be 100 times. So now you're seeing it kind of crimp up. And if I pause the animation, go to the deformed shape, this is the behavior of that model we're seeing. So it's deflecting inward, but it's trying to bend around those ribs. So if I'm actually looking at this deformed shape, this kind of makes sense to me. Now, again, we're not going to actually see this much deflection and warpage in the sheet metal. This is an exaggeration of it, but it allows you to kind of get a better way to confirm that this model is behaving the way you'd want. And I'm a big fan of, before you even start writing down magnitude values of stresses or displacements or anything like that, make sure the physics are behaving how you'd expect, or things moving that you want it to move, or things that aren't moving, not supposed to be moving. And what I like about this model is I'm seeing the pressure go, first off, the correct direction, but I'm seeing them want to wrap around those ribs correctly. That's why we introduced the ribs in the first place. And this makes sense to me. I could see this happening in the real world there. So a few other kind of final things just to make your life a little bit more clear with HyperView. I know it's not the cleanest software in the HyperWorks suite. A couple things I want to note here is the file open tool is a little funky. And when you open, it actually brings you down to the bottom of the tool. And it's going to have 2 fields. It's going to ask you to load in a model and a result. That's more of a legacy feature for back in the dark ages of the tool. Once upon a time, result files were not very detailed. They used to literally just be a list of, this is element 1, this is element 1's stress, this is element 1's displacement, and it would repeat for a million elements. The problem is with that definition is the result file on its own did not know the coordinate locations in the model of where element 1 was located. So a result file was just a list of results. It actually didn't contain model information like geometry or how it filled up space. So as a result of that limitation, you used to have to load in the model itself that had the elements correctly positioned, and the result file would overlay on top of that. In 2020, of course, things have been streamlined and are wonderful and are amazing. So what we have now is a more smarter result file that HyperWorks uses called the H3. We double click it. HyperView itself doesn't know how to load that application, but through this input reader, you can point to an H3D file as both the model and results. So I can just click this little Manila folder, find my H3D file of all those different results we got, and now I can hit apply to load that in. So that's what you load in. It's the H3D file. That is the result type from OptiStruct. And a few other things I can point to. If I actually go to that folder where I saved my our analysis that we ran together, I told you it's a convenient thing to get in the habit of making your own folder. Well, the reason for that is a typical OptiStruct run could yield as many as a dozen files for it. And a lot of this is stuff you're not going to be interested in. But a few things I want you to write down to get familiar with, or kind of a list of things to get familiar with, would be our out file and our FEM back. And we'll talk about why in a second here. So this is the checklist I'm going to send you guys here. Pardon me for just one moment. So you have your .h3d is the result file. Remember, it's multi-purpose doodad. You also have your .out file. This is a summary file. Any messages OptiStruct had for you during solving is listed in the out file. So I would recommend, while you're getting familiar with your first couple runs, open up this out file in something like a text editor or a notepad or whatever you prefer. And the out file tells you some good stuff. It tells you, first off, any warnings or errors are always saved in here. So if you accidentally close that OptiStruct dialog box and didn't see what went wrong, the out file will tell you. It also gives you a quick summary of things like the total number of elements and nodes and equations that were needed to be solved, as well as subcase information, memory usage. So this is more for commercial users that are interested in making sure they're not overriding their machines or overloading them or vice versa there. So it checks some hardware specs for you, but it also has down here the time it took to solve the job as well. So certainly as you get more experience in the heavy duty jobs, keeping track of how quickly you can solve something once they get out of the, typically once you get past an hour of runtime, that's going to be very relevant to you. Obviously, a 2-day solution is very different from a 5-day solution, or a 2-hour solution is very different from a 12-hour solution. So just kind of having an idea of how long these take to run, this is a great way to get that information. Now, the other final one you have in here, and certainly throughout the webinar series, I would never recommend you not to take any additional trainings with us. But if there was absolutely one more you signed up for, if you haven't already, I would very much recommend you attend some of our OptiStruct courses as well. We spent intentionally in this class a few days focusing solely on meshing and not as much on the physics side, because the OptiStruct specific trainings are going to pick up from those steps. So a lot of what we covered today with property cards, materials, load collectors, we go much more in detail in OptiStruct specific trainings to talk about all of those different OptiStruct entities. So HyperMesh class, what we had done here today is really more focused on that model building, discretization steps. There are many different solver classes we offer. And I would start with a simple OptiStruct linear analysis training to really start getting more familiar with what's happening in the solving side. So if you were interested kind of in a mini Hooke's Law lesson and wanted to get a better understanding of what's happening with my tools, why do I need to keep track of stiffness matrices or things like that, the OptiStruct class is really the next step that goes more into detail with those. So it's less button clicks and less meshing. In fact, from the OptiStruct training, I'm thinking of all of the exercise models pick up after the meshing steps. And it's a lot like the submarine hull of just setting up some physics, setting up some property cards or solution cards, and then reviewing your results and checking that you got the physics model correctly. So a lot of good stuff there. And why I bring that up now is the other file you should be familiar with and I mentioned this the other day, this is ultimately why we spend so much money on HyperMesh, or why Altair charges so much for it, is it writes out the FEM deck, or the OptiStruct input file. This is the text file that the solver reads in. So remember, OptiStruct doesn't read a HyperMesh model. OptiStruct reads this FEM file, which is a huge text file, and it's an actual ASCII formatted deck. When I was learning FEA, I learned it at a research institute in Texas that focuses on crash and transportation safety. The woman who taught me FEA used to do all of her analysis setup outside of pressure loadings and force loadings in the deck itself. So she would define her materials not through the HyperMesh GUI. She would come in here, find the section of this file, and there's all sorts of ways you can get good at coming through here. But she would just come into the section that defines her materials and by hand define that material. And the OptiStruct classes will help you learn these formats a little bit more. But as an example, my steel materials is defined in these 3 lines of text. I have material 1, known as steel. It's calling the Mat 1 card image. It has the first color red. 5, I'm off the top of my head, I can't remember what the 5 is calling, but here is my Young's modulus, here is my Poisson's ratio, and here is my density. So all of that definition is actually just saved in a text file that OptiStruct reads and spits out an even bigger text file that are your results. It is incredible to me that HyperMesh and HyperView have the graphics capabilities to list these millions of lines. And seriously, this is a relatively small model, and we got an 8,000 text file line input deck. These could be millions of lines. So it's so incredible to me that the graphics capabilities can display all of this on screen so quickly. So what I would recommend to you guys in the class before I let you guys get out of here, not that you aren't free to leave now, frankly, take a look at these student training files, and I would thumb through as you feel you need to. I feel pretty good about how I taught this week. So definitely on some things you feel that you want to get shored up on or review again, come into those student PDF slides and just spend, no more than a half hour on a chapter. And frankly, if you find some stuff that's being talked about in the slideshow that I didn't cover with you guys, feel free to put that on the back burner until you're kind of ready to start exploring some of the newer features or additional things we didn't cover in this class. But I really make sure you feel comfortable on the geometry, 2D meshing, and analysis setups, and if you need to, 3D meshing slideshows as well for the topics we talked about. Go back through those PDF slides. Don't spend all day. Limit yourself to a half hour per at most, and just go back and review those for some basic information. Now, as you have time that's available to you, could be tonight, could be 3 weeks from now, you know your schedule better than I do. The student manual and the student exercise folders have a variety of different tutorial exercises for each of those workflows. And as you come down here and you feel like you're getting pretty good at doing just the geometry stuff and just the meshing stuff on its own and want to graduate to putting it all together, the final thing I can recommend to you is in that student manual, there's a chapter 9 exercise called our capstone project. If we were doing this as a live training in person, I had you guys in my classroom, we'd order lunch together, we'd have a good time. This is what I say for the very end of class. So we'll traditionally, teach this class over the course of 4 or 5 days throughout the week. Could be as many as 40 hours. So you guys probably can see why we had to cram everything in 6 hours. You probably brains are just overloaded. We try to give it as much time as we can for commercial users, and I know it's tough here with the webinar series. But this chapter 9 capstone project is a really good kind of like a test or a self-evaluation tool to really see, am I picking up the concepts on my own? Because what this exercise is, it doesn't give you a true step-by-step, click-by-click guide like the other ones does. It just gives you a rough summary. So it says, hey, the first thing you should do is bring in that model. The next thing you should do is this, but it doesn't tell you exactly how to do that. So I generally find that if users can comfortably get through this, and it's okay if it takes you 2 or 3 tries, you got to clean up a few things at the end. But if you can get through this in a couple hours, and definitely, once you know how to do it, it's something you could probably do in 20 minutes or so after the first try. This is a really good graduating, quote unquote, exercise. Now, I'm not going to sit here and say you can't do this. you stink and you're never going to figure out. That's absolutely not the case. And I'd really discourage you guys from thinking of your success in such a binary way. But this is a really good kind of evaluation exercise I've used in the past. So if you're feeling confident while you're going through some of the more workflow specific exercises, there is one that's kind of a put it all together. And I'm warning you guys now though, and this is a bit of just a challenge with the class. There's definitely going to be some steps you guys hadn't seen from this class there. So I apologize in advance. You might want to go back through some of those other sections we either glossed through or skipped over entirely to get the gist of it. But this is one way you could try to think of a self-assessment for that. So with all of that said, I want to thank you guys for your patience throughout the last couple of days here. Sticking through here, especially today. I know we're almost 20 minutes over. So what I'm going to do here is very quickly save my analysis setup sheet for you guys, because this is a good one here. And I'm going to add this as an entity called a handout, if I can figure out how to do this here. And if not, I can always ask Darius and friends to send this out to you guys. Maybe that's what we're going to have to do here. I'm not seeing a way for me to submit this to you guys. I apologize about that. So I'll have a little a file sent out to you guys here for my little checklist there. I want to make sure you guys have access to that. So we'll get that sent out to everyone's emails. The same thing, I've got a question here for a link for the training materials. Yep, we got that shared there. We'll make sure that gets sent out there. Again, though, I'll be here for a few more minutes if there's any lingering questions, but sincerely thank you guys for wanting to be here. It makes me feel good seeing that the attendance numbers are almost the exact same, you know, Thursday, 20 minutes after the session as what it was when we started Monday morning. So I really appreciate that from you guys, and definitely let me know if there's anything else I can help with. But that said, get out of here, enjoy your weekends. For those of you on the Eastern Coast, go get some food, do what you got to do there. So thank you again, everyone. Enjoy your evenings. Hopefully I'll see you guys in some other future trainings.